Linear Algebra 2, Tutorial 8, Quadratic Forms. Problem 1. Which of the following expressions for the map Q from R3 to R defines a quadratic form? A. Q of x is equal to x1 squared plus x1 x2 minus x3 squared. B. Q of x is equal to 3x transpose times x. C. Q of x is equal to 1 minus x1 squared minus x2 squared. D. Q of x is equal to x1 squared plus x2 minus x3 squared. E. Q of x is equal to x transposed times the matrix 2, 1, 0, 1, 2, minus 9, 0, minus 9, minus 1 times x. F. Q of x is equal to x transposed times the matrix 0, minus 1, 1, 1, 0, 5, minus 1, minus 5, 0 times x. G. Q of x is equal to minus the inner product between x and x, where the inner product is just some inner product on R3. And H. Q of x is equal to the inner product of x and y, where we have some inner product on R3, and y is a fixed vector. Solution. Recall first that Q is a quadratic form if and only if we can write Q of x as x transposed times A times x for some matrix A whose size is dimension of V times dimension of V. So now let us look at each of these questions separately, one by one. So for A, we have the formula Q of x is equal to x1 squared plus x1 x2 minus x3 squared. In this case, we can write Q of x as x transposed times the matrix 1, 1, 0, 0, 0, 0, 0, 0, minus 1 times x. So this one corresponds to x1 squared, this one will give us x1, x2, and this minus 1 will give us minus x3 squared. So this Q is a quadratic form by definition. For question B, this is when Q of x is equal to 3x transposed times x. We can write Q of x as x transposed times 3 times the identity matrix times x. This expression is obviously equal to 3 times x transposed times x, because scalar matrices commute with all other matrices. Therefore, this Q is also a quadratic form by definition. For part C, Q of x is equal to 1 minus x1 squared minus x2 squared. From this formula, we know that Q of 0 is equal to 1. So if we plug in 0 here and here, we are left with 1. And 1 is not equal to 0. However, if we have a quadratic form written as x transpose times A times x, and we plug in 0 instead of x, we obviously get 0. So for any quadratic form Q, Q of 0 must be 0. Therefore, this expression does not define a quadratic form. Part D. So in this case, Q of x is equal to x1 squared plus x2 minus x3 squared. So let us assume that this is a quadratic form, and so it is written as x transpose times A times x for some matrix A. This is a 3 times 3 matrix with entries A, I, J. So let us compute both expressions for the vector E2, which is a vector 0, 1, 0. For the expression with the matrix, we will just get A22. For the expression with the formula, we just get 1. So A22 must be equal to 1. Now, if we compute both values for x equal to 2e2, for the expression with the matrix, we will get 4a22, which is 4. While for the expression with the formula, here we have only x2 without square, so we will get 2, and 4 is not equal to 2. So this is a contradiction, which proves that this expression does not define a quadratic form. Part E. This is the expression when Q of x is equal to x transposed times the matrix 2, 1, 0, 1, 2, minus 9, 0, minus 9, minus 1 times x. This is a quadratic form simply by definition. Part F, the expression q of x is equal to x transposed times the matrix 0, minus 1, 1, 1, 0, 5, minus 1, minus 5, 0 times x. Again, this is a quadratic form by definition. It is written as x transposed times some matrix times x. If we plug in concrete values of x and compute this expression, we will get 0, because 1 plus minus 1 is 0, minus 1 plus 1 is 0, and minus 5 plus 5 is 0. So this is just a fancy way to write down the zero quadratic form. Now let us look at part G. So here q of x is equal to minus the inner product of x with itself with respect to some fixed inner product on R3. Let us choose an orthonormal basis V in R3 for this inner product. We know that orthonormal bases exist. In this orthonormal basis, q of x will be written as the coordinates of x in the basis V transposed times the matrix minus the identity matrix times the coordinates of x in V, the usual coordinates. And hence this q is a quadratic form by definition. And finally, for part H, we have q of x is equal to x inner product with y, where we have some fixed inner product on R3 and some fixed vector y in R3. Again, we choose an orthonormal basis V in R for this inner product. So from the expression, we see that q of x in this orthonormal basis is equal to the transposed of x's coordinates in the basis V times y's coordinates in the basis V. Assume that we can write the same thing as the transpose of x's coordinates in the basis V times some 3 times 3 matrix A with entries aij times x's coordinates in the basis V. So this is what we need to check to determine whether q is a quadratic form. So assume first that y is equal to 0. If y is equal to 0, then q of x is equal to 0 for any x from this expression. The scalar product of anything with the 0 vector is 0. Therefore, this is a 0 map, and the 0 map is a quadratic form. We can take as its matrix the 0 matrix. So q of x is equal to x transpose times 0 times x. So if y is equal to 0, this does define a quadratic form. Now assume that y is not equal to 0. Then there exists I, the index between 1 and 3, such that the i's entry of the vector, which gives us y's coordinate in the basis V, is non-zero. Let's assume that this non-zero number is denoted by omega. It's a real number which is not 0. Then, if we evaluate our quadratic form at Vi using the matrix expression, we would get AII. And if we evaluate it using the inner product expression, we will get omega. So AII should be equal to omega, and this should be a non-zero real number. And now we evaluate the quadratic form at 2Vi. Using the matrix expression, this gives us 4 times AII, which is equal to 4 omega, and this is a non-zero real number. If we evaluate using the scalar product expression, we will get 2Vi, because we multiplied by 2 the vector x. And this is equal to 2 omega, because the scalar product is linear with respect to the first variable. And again, this is a non-zero real number. So we get 4 omega is equal to 2 omega, and omega is a non-zero number. We can cancel it and get 2 is equal to 4, a contradiction. This implies that in this case, our formula for q does not define a quadratic form. So this completes problem 1. Problem 2. Determine the symmetric matrix of the following quadratic forms on R3 in the standard basis. Part A of x is equal to x1 squared plus 2x2 squared plus 3x3 squared. Part B of x is equal to x1 x2 plus 5 x1 x3 minus 2 x2 x3. Part C, C of x is equal to x transposed times the matrix 1, 2, 3, 0, 2, 1, 1, minus 1, 0 times x. Solution. For part A, we have the formula x1 squared plus 2x2 squared plus 3x3 squared. So we only have coefficients at squares. So we write these coefficients on the diagonal. So the position 1, 1 corresponds to the coefficient at x1 squared, which is 1. The position 2, 2 corresponds to the coefficient at x2 squared, which is 2. And the position 3, 3 corresponds to the coefficient at x3 squared, which is 3. And all other coefficients are 0. This is the matrix of the quadratic form A in the standard basis. For part B, we have the form x1, x2 plus 5x1, x3 minus 2x2, x3. So we should take the coefficient at x1, x2, and in order to write the symmetric matrix, we should split this coefficient into halves. And then write these equal halves of this coefficient in the entries I, j and j, I of our matrix. So there are no coefficients at squares, so the diagonal is 0. We have coefficient 1 for x1, x2, so we have 1 half in position 1, 2, and we have 1 half in position 2, 1. We have coefficient 5 for x1, x3, so we have 5 divided by 2 in position 1, 3, and we have 5 divided by 2 in position 3, 1. Finally, we have the coefficient minus 2 at x2, x3, so this gives us minus 1 in position 2, 3, and minus 1 in position 3, 2. So the matrix of B in the standard basis is the matrix 0, 1 half, 5 divided by 2, 1 half, 0, minus 1, 5 divided by 2, minus 1, 0. And finally, for part C, we have C of x is x transposed times the matrix 1, 2, 3, 0, 2, 1, 1, minus 1, 0 times x. So the coefficient at xi, xj for the formula expression of this quadratic form would be the sum of the coefficients in positions ij and ji of this matrix. So we should take this coefficient and then, similarly to the previous case, split it in 2 equal halves and write in the new entries ij and ji. So here is the outcome. The matrix of C in the standard basis is the following matrix. The diagonal is the same. So it was 1, 2, 0 here. It's 1, 2, 0 here. Now positions 1, 2, and 2, 1. We had 2 here and 0 here. We add them up. We get 2. We split it in 2 equal parts. It's 1 and 1. And so we write 1 in position 1, 2, and 1 in position 2, 1. Positions 1, 3, and 3, 1. We have 1 here and 3 here. Their sum is 4. Splitting it in equal parts, we get 2 and 2. So we write 2 in position 1, 3, and 2 in position 3, 1. And finally, positions 2, 3, and 3, 2. We had minus 1 and 1. Their sum is 0. So we should divide 0 in 2 equal parts. It's 0 plus 0. So we write 0 in position 2, 3, and 0 in position 3, 2. And the answer is the matrix 1, 1, 2, 1, 2, 0, 2, 0, 0. And this completes problem 2. Problem 3. Consider the following two quadratic forms on E2. P of x is the form x1 squared plus 2x1 x2 plus 2x2 squared. And Q of x is the form x1 squared plus 6x1 x2 plus 6x2 squared. Find a basis in E2 which diagonalizes both forms simultaneously. Solution. This problem is only guaranteed to be solvable if one of these forms is positive definite. So let's determine whether one of these forms is positive definite. For this, we need to determine the signature of the one which is positive definite. So let's start with P and see whether it will work out. To determine the signature, the easiest is to complete the square. So we take the expression x1 squared plus 2x1 x2 plus 2x2 squared. Here we have two summands with x1 squared plus 2x1 x2. So we write x1 plus half of this coefficient. So this is 1 times x2 squared. This expression will give us these two summands back, plus the extra summand x2 squared, for which we compensate by subtracting x2 squared. So now this expression is equal to x1 squared plus 2x1 x2. And then we copy the rest, which is 2x2 squared. And now when we add this, we get x1 plus x2 squared plus x2 squared. We have now the sum of two squares with positive coefficients. This means that the form P has signature 2, 0 and hence is positive definite. Great, so the form P is positive definite, so this problem is solvable. So now let's solve it. We can write P as P of y equal to y1 squared plus y2 squared, where y1 and y2 are the coordinates corresponding to the base change such that y1 is x1 plus x2 and y2 is x2. Then we compute the base change in the opposite direction, so x2 is equal to y2 and x1 is equal to y1 minus x2, which is y1 minus y2. So if we set v1 to be the vector e1 and v2 to be the vector minus e1 plus e2, then for any vector w, which has in the standard basis coordinates x1 and x2, then this vector has coordinates y1 and y2 in the basis v. And we have the transformation matrix from the standard basis to the basis v, which is equal to 1 minus 1, 0, 1. We denote this matrix by T. So how to check this? So the base change formula, the standard coordinates are equal T times coordinates in V. And if you multiply y1, y2 on the right with this matrix, we will get x1 is equal to y1 minus y2 and x2 is equal to y2. So this is a correct transformation matrix from the standard basis to our new basis V, which corresponds to the set y of new coordinates. So now let us compute the expression for the quadratic form Q in these new coordinates. So Q of x is equal to x1 squared plus 6 x1 x2 plus 6 x2 squared. We know that x1 is y1 minus y2 and x2 is y2. So we can write the same thing as y1 minus y2 squared plus 6 times y1 minus y2 times y2 plus 6y2 squared. Consequently, Q of y is equal to y1 squared from here, plus, so we have minus 2 here and plus 6 here, plus 4 y1 y2, and then 1y2 minus 6 and plus 6, so plus 1 y2 squared. So this is the expression for the formula Q in the coordinates y. Now we can take this expression and write the matrix of the form Q in the basis V. So this matrix is a matrix 1, 2, 2, 1. So this is because the expression, the coefficients are 1. This goes into position 1, 1. The 1 at y2 squared goes to position 2, 2. And the 4, the coefficient for y1, y2, is split into two equal parts, 2 and 2, and is written in the positions 1, 2 and 2, 1. So let's denote this matrix by Q, the matrix 1, 2, 2, 1. This is the matrix of the quadratic form Q in the basis V. Now, we can consider R2 as an Euclidean space with the inner product for which our new basis V is an orthonormal basis. Then we know that the expression for the quadratic form P, recall that the quadratic form P is equal to y1 squared plus y2 squared. So we can write this as the coordinates of a vector transposed times the coordinates of the vector. And this is true for any w. And what we can do, we can now diagonalize the second quadratic form Q in an orthonormal basis. And when we do the orthonormal change of basis, this will not change the expression for P because of the base change formula. We will have here in the middle the transformation matrix transposed times the transformation matrix. But for the base change between two orthonormal bases, the transformation matrix is orthogonal. And so the transpose is the inverse. So they will cancel out, and the form for P will be the same. So now let's try to diagonalize our matrix 1, 2 to 1 in an orthonormal basis. We start with a characteristic polynomial. So we take the determinant of this matrix, subtracting minus lambda on the diagonal. So we have the determinant of 1 minus lambda, 2, 2, 1 minus lambda. This is equal to 1 minus lambda squared minus 2 squared, and this is equal to 1 minus lambda minus 2 times 1 minus lambda plus 2. So the characteristic polynomial is equal to minus 1 minus lambda times 3 minus lambda. The eigenvalues here are minus 1 and 3, and both with algebraic multiplicity 1. So now let's determine the eigenvectors. The eigenvectors for the first eigenvalue, minus 1, are the solutions to the homogeneous system of linear equations with matrix, which you obtain when you take the matrix of the quadratic form and subtract minus 1 on the main diagonal. So we get the matrix 2, 2, 2, 2. And here it's easy to guess that 1 minus 1 is a solution, because if we multiply, we get 2 minus 2 is 0, 2 minus 2 is 0. Since the algebraic multiplicity of this eigenvalue is 1, this solution is unique up to scalar. And we have to norm it. Its length is the square root of 2, so we take the vector b1 to be 1 divided by the square root of 2, 1 minus 1. So this is our first basis vector in an orthonormal basis. We have also the second eigenvalue, 3, and the eigenvectors for this eigenvalue are the solutions to the homogeneous system of linear equations, whose matrix we get if we take the matrix of the quadratic form and subtract 3 on the main diagonal. And this gives us the matrix minus 2, 2, 2, minus 2. And here it's easy to guess that the vector 1, 1 is a solution, because the sum in each row is 0. So we have the vector b1, which is 1, 1. This is a solution. Since the algebraic multiplicity is 1, this solution is unique up to scalar. And again, it has lengths root of 2. So if we divide by the lengths, we get a normed vector, which we denote by b2, which is equal to 1 divided by the root of 2, 1, 1. So this gives us the answer that the diagonal form of our symmetric matrix is the matrix minus 1, 0, 0, 3. So it's a diagonal matrix with eigenvalues on the diagonal. And the transformation matrix is the matrix of the corresponding eigenvectors. So it's 1 divided by root of 2 times the first column is 1 minus 1. This is the eigenvector for minus 1. And then the second column is 1, 1. This is an eigenvector for 3. So this is a transformation matrix from the basis V, our original orthonormal basis, to the new basis B, where the second form Q has this diagonal form. So in this new basis, and let us denote the coordinates in this basis by Z1 and Z2, so we have that the quadratic form P has the standard inner product form Z1 squared plus Z2 squared. So it's the same form as in the original orthonormal basis, but for the new coordinates. And the quadratic form Q has the form minus Z1 squared, this is because this minus 1, plus 3Z2 squared. This is because of this 3. It remains to find the transformation matrix to this basis from the standard basis. Note that this is a transformation matrix from V to the basis B. But this is a product of the transformation matrix from E to V times the transformation matrix from V to B. So the first one is 1 minus 1, 0, 1. The second one is 1 divided by the root of 2, 1, 1 minus 1, 1. When we multiply, we will get 1 divided by the root of 2. So here, 1 plus minus 1 squared, 2, 1 minus 1, 0, and then here minus 1, 1. So this is a transformation matrix from the standard basis to the bases in which both formed are diagonalized. So this completes problem 3. Problem 4. Diagonalize in an orthonormal basis and determine the signature of the quadratic form on E4 given by the following matrix in the standard basis. The matrix Q is 3, 2, 1, 1, 2, 3, 1, 1, 1, 1, 3, 2, 1, 1, 2, 3. Solution. First, we need to determine the characteristic polynomial for this matrix. So we take this matrix, subtract x on the main diagonal, and compute the determinant. So in order to compute this determinant, let us note that the sum in all columns is the same. So if we add 3 minus x plus 2 plus 1 plus 1, we get 7 minus x. We have 7 minus x here, 7 minus x here, and 7 minus x here. So the first row is 7 minus x, 7 minus x, 7 minus x, 7 minus x. So we take the 7 minus x out, we get 1, 1, 1, 1, 2, 3 minus x, 1, 1, 1, 1, 3 minus x, 2, 1, 1, 2, 3 minus x. So this is our new determinant. Now we can use this one to kill everything in the first column. So we subtract row 1 from rows 3 and 4, and we subtract twice row 1 from row 2. This does not change the determinant. So we get 7 minus x. The first row is the same, 1, 1, 1, 1. The second row becomes 0, then here 1 minus x, here minus 1, minus 1. The third row becomes 0, 0, 2 minus x, 1. And the last row is 1, 1, 1, 2 minus x. And now we see that this is a block diagonal matrix with 1 times 1 block here, 1 times 1 block here, and 2 times 2 block here. So the determinant is the product of 1, 1 minus x, and this 2 times 2 determinant, which is 2 minus x squared minus 1. So we get the expression 7 minus x times 1 minus x times 2 minus x squared minus 1. And this is 2 minus x minus 1 times 2 minus x plus 1. So altogether, we get 7 minus x times 3 minus x times 1 minus x squared. So we have 3 eigenvalues. The eigenvalue lambda 1 is equal to 1 with algebraic multiplicity 2. The eigenvalue lambda 2 is equal to 3 with algebraic multiplicity 1. And the eigenvalue lambda 3 is equal to 7 with algebraic multiplicity 1. The eigenvectors for the first eigenvalue lambda 1 is equal to 1 are the solutions to the homogeneous system of linear equations whose matrix is obtained from the matrix of the quadratic form by subtracting 1 on the main diagonal. So we get the matrix 2, 2, 1, 1, 2, 2, 1, 1, 1, 1, 2, 2, 1, 1, 2, 2. We see that rows 1 and 2 are the same. We delete one of them. Rows 3 and 4 are the same. We delete one of them, and we swap the outcomes. So we get 1, 1, 2, 2, 2, 2, 1, 1. So now we multiply the first row with minus 2 and add to the second row. We get 1, 1, 2, 2, 0, 0, minus 3, minus 3. So now we can divide the second row by minus 3, so it becomes 0, 0, 1, 1. And now we multiply it with minus 2 and add to the first row. And we get the matrix 1, 1, 0, 0, 0, 0, 1, 1. Here again, it's easy to guess two linearly independent solutions, 1 minus 1, 0, 0, which we denote by V1, and 0, 0, 1, minus 1, which we denote by V2. Note that they both are orthogonal to each other, so we need only to norm them. So we get W1 is 1 divided by the root of 2 times 1 minus 1, 0, 0. The length of this vector 1 minus 1, 0, 0 is root of 2. And similarly, W2 is 1 divided by the root of 2, 0, 0, 1, minus 1. The second eigenvalue is 3, so the corresponding eigenvectors are the solutions to the homogeneous system of linear equations with matrix 0, 2, 1, 1, 2, 0, 1, 1, 1, 1, 0, 2, 1, 1, 2, 0. And here it's easy to guess that the vector 1, 1, minus 1, minus 1 is a solution. because 1, 1, minus 1, minus 1. 2 minus 1 minus 1 is 0. 2 minus 1 minus 1 is 0. 1 plus 1 minus 2 is 0. 1 plus 1 minus 2 is 0. So this vector is a solution. Since our algebraic multiplicity is 1, it's a unique solution, and it has length 2. So if we norm it, we get the vector W3, which is 1 divided by 2, 1, 1, minus 1, minus 1. Finally, the eigenvectors for the eigenvalue 7 are the solutions to the homogeneous system of linear equations with the matrix minus 4, 2, 1, 1, 2, minus 4, 1, 1, 1, 1, minus 4, 2, 1, 1, 2, minus 4. And here we can note that the sum of elements in each row is 0. This means that the vector 1, 1, 1, 1 is a solution. Again, the algebraic multiplicity is 1, so it's a unique solution up to scalar. It has length 2, so again we norm it and get the vector W4, which is equal to 1 divided by 2, 1, 1, 1, 1. So now we can write down the answer. So the diagonal form is a diagonal matrix with our eigenvalues on the main diagonal, and eigenvalues should be repeated as many times as the algebraic or geometric multiplicity. So we have 1, 1, 3, 7 on the diagonal of this diagonal matrix. And the transformation matrix is the matrix of the corresponding eigenvectors. So we take out 1 divided by 2, and then the first eigenvector is root of 2 minus root of 2, 0, 0. This is an eigenvector with eigenvalue 1. Then we have 0, 0, root of 2 minus root of 2. This is an eigenvector with eigenvalue 1. So these roots of 2 are because this scalar 1 divided by 2, which is taken out. Then the third column is the eigenvector with the eigenvalue 3, which is 1, 1, minus 1, minus 1. And the last column is the eigenvector with the eigenvalue 7, which is 1, 1, 1, 1. And since all eigenvalues are positive, the signature of this quadratic form is 4, 0. And this completes problem 4. Here are some additional problems and questions. Question 1. Determine the signature of the quadratic form x1 squared minus 2x1 x2 plus 4x3 x4 plus x4 squared on R4. Question 2. Diagonalize the quadratic form 2x1 squared minus x1 x2 plus x1 x3 minus x3 squared plus 2x2 x3 minus x2 x4 plus x4 squared on R4. Question 3. Diagonalize in an orthonormal basis the quadratic form 2x1 squared plus 2x2 squared plus 2x3 squared minus 2x1 x2 minus 2x1 x3 minus 2x2 x3 on E3. Question 4. Diagonalize in an orthonormal basis the quadratic form 4x1 minus 3x2 times x2 on E2. And finally, question 5. What is the signature of the quadratic form on the set of all polynomials of degree at most 3, where the value of the quadratic form q at a polynomial f of x is given by the formula integral from 0 to 1 f of x squared dx. Thank you very much, and see you next time.